guys, it's Miss Martinez, and in this video we are looking at arithmetic series and sigma notation. The objectives for you are to be able to find the sum of an arithmetic series, to apply the formulas for the sum of an arithmetic sequence to solve problems, to expand, evaluate, or write a series in sigma notation. And I wanted to start with this problem. This is a classic problem. There was a little boy named Carl Goss, and he was born long time ago. And at age 10, his teacher gave him a problem, and I'm pretty sure it was that day, you know, when the teachers are just like really tired and they don't want to hear the little 10-year-olds' voices, and so they gave them a problem that they thought would take a long time, and suddenly, like, okay, so a minute later, and little Carl's like, I have the answer, miss, and she's like, no, or he's like, no, because this would take you a lot longer, and actually he figured out a way to solve it and did it really quickly, and then that teacher was probably really frustrated, but also super impressed with this little boy genius. So here was the question. The question the teacher gave was, find the sum of all the whole numbers between 1 and 100. And this was, you know, a couple hundred years ago, and there were not calculators to be able to do this, and so he was just doing this like arithmetic by hand. So this is what he did. He figured out a pattern. He said, okay, if I take the first number and the last number, gives me 101. And if I move in and do 2 plus 99, it gives me 101. And if I keep doing that and keep moving in and taking like the first and the last move in, the second and the second to last move in, the third and third to last, all the way until those middle two numbers, 50 and 51, it's going to give me 101 every single time. And so he said, okay, well, how many pairs am I going to have? I'm going to have 50 pairs like this. And so 50 times the sum of each of those pairs, which is 101, is 5,050. And that's how he solved the problem. And that is why he is a famous mathematician, because already at the age of 10, he was doing this type of mathematics. A series is a word to describe the sum of terms of a sequence. So when you add up all the terms in a sequence, that is called a series. So we're going to write and evaluate the series related to this sequence. We are going to be adding 5 terms, and so we would write it S, a large S for series, of the 5 terms, so we'd put a little subscript 5, and we would just be adding those together. It is really just that easy. And if you added those up, you would have 40. That's it. The sum of those 5 terms in the sequence S sub 5 is 40. Now I want us to look a little bit more at that problem by little Carl Goss. The sum of those 100 terms, S sub 100, that would be 1, 2, 3, all the way to 100. Imagine if we wrote that again and added these together. Just follow along with me here. It's not going to be real clear at the beginning, but I'm going to show you a formula that we can derive from this. What would happen if we do this? Well, on the right-hand side, we're going to see, like we had talked about earlier, it's going to be 101 all 50 times, or I'm sorry, all 100 times, right? Because we're going to start with 1 and 100, 2 and 99. So this goes, there's 100 terms up here and 100 terms down here. We're adding all of those 100 terms. So this is 100 101s. And if you add these together, I'll have 2 sums of 100 terms. So again, condensing this, I have 100 sums of 101. It's a little bit easier than writing it 100 times. Now what have I done? I've taken and divided each side by 2, so now this is 50 times the sum of really what is just the first and last term. Half of the number of terms that I'm adding up times the sum of the first and the last, which is what we already know to be true, 5,050 for the Arg2 problem. Now I showed you that because an arithmetic series, for an arithmetic series, that is the sum of some number of n terms in an arithmetic sequence with a common difference, right? Because arithmetic means you're adding, you'll have a common difference. That formula looks like what we just saw in the Arg2 problem. The sum of those n terms is going to be the number of terms divided by 2 times the sum of the first and last term. Now, if we didn't have the last term, you would just use the formula to find an. Remember, an is a1 plus n minus n1 times d. That's why now we have 2 a1s. So I've just substituted in what an is equivalent to. It is a1 plus n minus 1 times d. So either one of these works. This one is nice if you know the first and last term. This one would be what you would use if you only knew your first term and your difference. So let's find the sum of 150 terms for this sequence. Now, do I know what my 150th term is? No. And do I want to go as far as to try and write all 150 terms? No. So what I will do is I'm going to identify what I do know. I know that my first term is 7. There it is. My common difference is 4, adding 4, adding 4. And the nth position, what I'm going up to, is 150. I am now going to substitute these into the formula that we are given. And I'm using that second formula from above because I don't know what my 150th term is. So the sum of my 150 terms is 150, which is my n, divided by 2, times my first term times 2, that's 7 times 2, n minus 1, that's 150 minus 1 times that common difference. I'm going to simplify. Half of 150 is 75. The product here is 14. I'm looking at this difference, which is 149 and 4. And if I plugged all that into my calculator, I want you to try it as well. You should get 45,750. And that is carrying out our objective of using our formulas to find the sum of an arithmetic series. All right, now let's find the first 3 terms of an arithmetic sequence, given that the first term is 4 and the sum of 7 terms, that's what this means, the sum or the series of 7, the sum of the 7 terms is 91. Okay, now this might seem crazy. How am I going to find my next 2 terms if I don't know my difference? That's really what we need, right? It's an arithmetic sequence, but I don't know the difference between my first and my second and my second and my third. That's what we need to find. So we're gonna use our formula to find a series and solve for D. The sum of the 7 terms, in being 7, that's going to be 7 divided by 2, 2 times my first term, which is 4, in minus 1, that's 7 minus 1, and I don't know D. That is what I'm solving for. S7 is 91. The product here is 8. The difference here is 6. Multiply each side by the reciprocal. So 91 times 2/7 is 26. And then we're going to keep going here. We will go ahead and subtract 8. That gives us 18. Divide by 6, and that gives us 3. The common difference here is 3, which means to find the next terms, we're just going to add that common difference. A1 is 4. A2 would be 3 more than that, which is 7. And A3 is going to be 3 more than the previous, which will give us 10. All right, I want to just conclude with a little bit about sigma notation. Here, when you see this sigma, it's a Greek letter. And down here at the bottom, this K value, that is our index, and it is our lower boundary. It's our first value that we're going to start with. This number up here is our last value, and is often called the upper bound. And A sub K, that is going to be your sequence's explicit form. So you're going to want to write the sequence in its explicit form such that then you'd just be able to plug in the position A1, A2, A3, all the way to AN. And this sigma right here, what that means is find the sum beginning at 1 up to this number for this sequence. And that's what I've written here, the sum of AK from K equaling 1 to N. That's what this means. Where the variable K is what we call the index of summation. Let's try some together. We're going to expand and evaluate. To expand this, we're beginning at 1. We're going to plug 1 in for K, and we're going to plug then 2 and 3 and 4 all the way to 5. So that would look like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Square each of those. That's 1, 4, 9, 16, 25. When added, that gives you 55. Another one here. Let's expand and evaluate this sum. So this is a nice explicit arithmetic sequence. You can tell here that we're looking at a difference. All right, or I should say a sum. So we're going to, though, begin at 2. So when we plug in, we'll plug in 2. And then we'll plug in 3 for K, 4 for K, and lastly 5 for K. And then we'd simplify each of these, and you would want to show all of your work here. The sum here is -5, -9, -13, -17, which when you do subtract all those, it would be -44.